Hello, welcome to Unix Programming Module 3, Lecture Series 3. So here in this Lecture 3, you are going to learn file and record locking, directory file APIs, device file APIs, FIFO file APIs, symbolic link file APIs. Okay, the first one is file and record locking. So Unix system allows multiple processes to read and write the same file concurrently, which provides data sharing among the process. So as you know, so here in the Unix system there will be more than one files available. Okay, so that file is shared between the more than one process. So while accessing the file, the data is shared among the process. It also renders difficulty for any process in determining which data and when data in a file can be overridden by another process. Okay, so in this case, so it is very difficult to determine when that data in a file can be overridden by any other processes. To overcome this drawback, Unix and POSIX systems support file locking mechanism. Okay, so if you want to avoid that, so you need to use that file locking mechanism. That mechanism is present in the Unix system. So using that, so you can avoid sharing the data between the process. So file locking is applicable only for regular file. So if you want to use that file and record locking, so you have to use this mechanism only to the regular file. It allows a process to impose a lock on a file so that other process cannot modify the file until it is unlocked by the process. Okay, so here file locking means a process can impose a lock. Okay, so it means that the process can set a lock on a file. Okay, so once the file is locked by particular process, the other process cannot access that same file until the process unlock the lock. Okay, a process can impose a write lock or read lock on either portion of a file or an entire file. So here a process can impose a write lock or read lock. So if a process set a write lock, okay, so other process only can read. Okay, so if a process set a read lock, the other process can write. Okay, a process can set these to lock either a portion of a file or the entire file content. A write lock is also known as a exclusive lock, and read lock is also called as a shared lock. Mandatory lock. Mandatory locks are enforced by an operating system kernel. If a mandatory exclusive lock is set on a file, no process can use the read or write system calls to access the data on the locked region. So here, if the mandatory exclusive lock is set on a particular file, okay, so other process cannot use read and write system call to access the data on the locked region. If a mandatory shared lock is set on a region of a file, no process can use the write system call to modify the locked region. Okay, see the difference here. The mandatory exclusive lock is set. Okay, no other process can use the read or write system call. So if a mandatory shared lock is set, no other process can use a write system call. Okay, so in a shared lock, the other process can use the read system call, okay, to read the content, but cannot use the write system call to modify that in case of shared lock. So in case of mandatory exclusive lock, the process cannot use read and write system call to access the data. mandatory locks may cause some problems. So what is that? So if a runaway process sets a mandatory exclusive lock on a file and never unlocks that lock, no other process can access the locked region of the file until either the runaway process is killed or the system is reboot. Okay, so here once the process is using mandatory exclusive lock, okay, to access that file, so after accessing the file, the process should release the lock. So otherwise the other process cannot access the same file. Okay, so if the process doesn't remove it, okay, the process need to be killed or the system should reboot. Then only the mandatory exclusive lock will be released. Advisory lock. An advisory lock is not enforced by the kernel at the system call level. Okay, so mandatory lock is enforced by the kernel, but advisory lock is not enforced by a kernel at the system call level. This means that when the lock may be set on a file, other process can still use the read or write APIs to access the file. So here in advisory lock, so if a file is locked by any of the process, the other process can use the read or write API to access the same file. That is the difference between mandatory lock and advisory lock. To make use of advisory locks, processes that manipulate the same file must cooperate such that they follow this procedure for every read or write operation to the file. So here in a Unix system, if any process is using advisory lock on a file, there should be a cooperation between the process to access the file, to read and write the content into the file. So what are the procedure need to follow by the process if they want to set advisory lock on a file? The first one is try to set a lock at the region to be accessed. So if this fails, a process can either wait for the lock request to become a successful or go do something else and try to lock the file again later. Okay, so here the first procedure is try to set a lock at the particular region to be accessed. Okay, the process is trying to lock the portion of a file. Okay, while setting a lock, if the process failed, okay, the process need to wait, because already the particular portion of the file is locked by other process. That's what. Okay, this process need to wait or do something. Second one, after lock is acquired successfully, read or write the locked region, release the lock, must follow the above file locking procedure to be cooperative. Okay, so once the process lock the file, read or write the locked region, release the lock. Okay, the process should release the read and write. All Unix systems support advisory locks. So here in a Unix system, so it support advisory locks. Unix system 5 use the FCNTL API for file locking. Okay, so Unix system version 5, so it uses the API FCNTL, file control API, for file locking. The prototype of the FCNTL API is #include fcntl.h, int fcntl, int file descriptor, the first argument, second argument int command flag, third argument is ... The file descriptor argument is a file descriptor for a file to be processed. The first argument is the file descriptor, so which will be pointing to a file once the file is opened. The second argument is the command flag, so which defines the operation is to be performed. Okay, so it defines which operation to be performed on a file. Okay, so here for the second argument there are three different value. The first one is a f underscore set lock, sets a file lock, do not block if this cannot succeed immediately. So this value sets a file lock, okay, and it doesn't block that. Second one, f set lock w sets a file lock and blocks the calling process until the lock is acquired. So if used f underscore set lock w, so it sets a file lock and blocks the calling process. Okay, so other process cannot access that until the lock is released. That is the difference here, set lock and the set lock w. Set lock sets a file lock and it doesn't block it. Set lock w, it sets a file lock and it blocks the calling process. Third one, f get lock, queries as to which the process locked on a particular file. Okay, so using this flag value, so you can get the process which locked the file. For file locking, the third argument of the FCNTL is an address of a structure's lock. This variable so gives the file where the lock is to be set or unset or queried. So here the third argument is, that is the address of struct, that is the structure is flock. The struct flock is declared in the fcntl.h. So this is the structure you need to use in the API fcntl as a third argument. Struct flock, so which contain 5 different value. The first one is the L type, what lock to be set or unlock. Second one, L vents, a reference address for the next field. L start, offset from the L vents, reference address. Length, how many bytes in the locked region. PID, that is PID of a process which has locked the file. Okay, the first one is the type. So here there are 3 different types. The first one is read lock, write lock and unlock. So here we can use any one of these 3. Okay, whether you want to set a read lock or whether you want to set a write lock and whether you want to unlock the file. So here the second is vents. There are 4 different values for the vents: seek current, seek set, seek end. Okay, so the seek current means the value is added to the current file pointer address from where you want to lock the file. Okay, from the current position or from the beginning, that is from the byte 0 or from the end of the file. Based on that you can use any one of the value to the vents variable. Okay, there are 3: seek current, seek set and seek end. Okay, the third is a start. Okay, from where you want to start, and length, how many bytes you want to lock in the file, and PID. Next one is a directory file APIs. Directory files in a Unix and POSIX system are used to help users in organizing their files into some structure based on the specific use of file. Okay, so here using a directory file APIs, you can organize all your files into some structure. They are also used by the operating system to convert file path names to their INO number. Okay, so here based on that INO number, so we can organize that. Okay, so if you want to access any file from the directory, so using that INO number, so you can access that instead of path name, because so here it converts path name to their inode number. For each file in the directory, there will be a inode number. Directory files are created in a BST Unix and a POSIX.1 by mkdir API. Okay, so here we are using that API mkdir to create a directory and organize all your file. Okay, so here there are two APIs in a directory file. The first one is a mkdir, so which creates a directory. Second one is a rmdir, which removes the directory from the file system. Okay, so the first mkdir, so it has two arguments. The first one is a constant char star path name. Second argument is the mode underscore t mode. Okay, and second API rmdir, so which has only one argument, that is a path name, so which directory you want to remove. The first argument, the path name argument, is the path name of a directory to be created. Second argument, the mode argument, specifies the access permission for the owner, group and others to be assigned to the file. Okay, we are using here the different modes. Okay, so if the API is accessed in creating a directory or removing a directory, the API returns 0, otherwise returns -1. So Unix system version 3, so which uses the API mknode to create a directory file. Okay, so version 3 of the Unix system is using that mknode API, but here Unix system 5, it is using mkdir in creating a directory. So Unix system version v.4 supports both mkdir and mknode APIs for creating directory files. Now, what is the difference between mkdir and mknode? Both creates directory in a Unix file system. The difference between these two APIs is that the directory created by the mknode doesn't contain dot and dot links. On the other hand, a directory created by the mkdir has the dot and dot links created. Okay, that is the difference between these two. Okay, dot and dot means root and parent directory is present. Okay, when you created a directory by using API mkdir, but that is, these two are not there in a mknode. A directory file is a record oriented file where each record stores a file name and the mode number of a file that resides in that directory. Okay, so here once you create a directory, the directory is a record oriented, so where you can store all your files. Okay, the following portable functions are defined for directory file browsing. These functions are defined in both dirent.h or system/dir.h headers. Okay, so this is the syntax or different API you need to use if you want to work with the directory files. Okay, the first one is open dir to open the directory, read dir to read the directory content, close dir to close that directory, and rewind dir. So if you want to rewind that directory from the beginning. Okay, so before that, so we need to include this header file system/types.h or system/dir.h and the structure. The use of these functions are: the first one, opendir opens a directory file for read only. Readdir reads a record from a directory file referenced by dir file descriptor and returns the content of the file or returns that record information. Closedir closes the directory file referenced by the directory. Rewind resets the file pointer to the beginning of the directory file referenced by the file descriptor. Telldir returns the file pointer of a given file descriptor. Seekdir changes the file pointer of a given file descriptor to a specified address. Seekdir. So where you want to start, so it gives the position. Next topic is device file APIs. Device files are used to interface physical devices with the application program. So when a process reads or writes to a device file, the kernel uses the major and minor device numbers of a file to select a device driver function to carry out the actual data transfer. Okay, so here in the Unix system, so if you connect any physical device, so if you want to access the data from that device, then so here, so you need to use the device file APIs in your application program. So through that you can access all the data from the device connected to the system. Okay, so here the kernel uses the major and minor number of the file, okay, to select the device driver function. So here in the Unix system, there will be more than one device driver functions will be available, okay, based on the major and minor number. Okay, so the kernel uses the major and minor number of the particular file, okay, and then you can use the driver function in an application program to access the actual data or transfer the data between the device and the system. Device files may be character based or block based. So here in a device file there are two types. First one is the character based device file, second is a block based. So Unix system defined the mknode API to create device file. Okay, so here you need to use the API mknode. So this is the syntax for the API. So you need to include header file system/stat.h and unistandard.h. Int mknode, there are three arguments. First one is the constant char star path name, mode and device ID. The first argument, the path name argument is the path name of directory to be created. You have to give here the path name. The mode argument specifies the access permission for the owner, group and others to be assigned to the file. Third one, that is the device ID, contains the major and minor device numbers and is constructed in the most Unix system as follows. The lowest byte of the device ID is set to a minor device number and the next byte is set to the major device number. Okay, so here if you want to transfer the data between the system and the device, okay, then you should know the major and minor device number and the driver function. Okay, so using them in your application program, then you can transfer the actual data between the Unix system and the device. One example here, to create a block device file called SCSI5. So this is one example for the block device file, and major numbers are, major number is a 15 for this device and minor number is a 3. Okay, so using these two in your application program, so you can access, read and write and execute. Okay, so using that API mknode. Okay, so this is how you can use that mknode to transfer the data, okay, between the block device file and the Unix system. Okay, so first you have to give here the device file name, that is SCSI5, okay, and then here you are given the mode, okay, and this is for file block, okay. First mode is the blocking, and read, write, execute for the users, group and others. You are giving all the permission to access the file, okay, and here we are using that device ID contain a major and a minor number. See, so 15, 8 and 13, okay. So using this, so we can transfer the data between the device file and the Unix system. But you should know here major and minor number of the device file, then only you can use the mknode API in your application program to transfer the data. Next one is the FIFO file APIs, first in first out file APIs. First in first out file are sometimes called as a named pipe, okay, so you can call this as a named pipe also. Pipes can be used only between the related processes when a common ancestor has created the pipe, okay, so you can use that pipe so only between the related processes. So creating a first in first out FIFO is similar to creating a file, okay. So here you need to use the API mkFIFO, okay. So int mkFIFO, so first argument is the constant character star path name and the mode. The first argument path name of a file to be created, second argument is the mode, okay, that is the access permission given for the user, group and others, as well as the s_i FIFO flag to indicate that is a FIFO file. So here along with the mode permission you need to use the flag, that is s_i FIFO, that indicates the file is a FIFO. So if the API is executed successfully, then returns 0, otherwise returns -1. So this is one example. So how to use that API in your application program, okay. So the API name mkFIFO and FIFO file is the file name to be created, okay, and here you are using that all the mode. The first is the s_i FIFO to indicate that is a FIFO file, and then you are giving the permission for user, group and others, okay. Another method to create a FIFO file for interprocess communication is to use the pipe system call, okay. So if you want the two processes communicates with each other to transfer the data between them, okay, then so you need to use the pipe, okay. So it has a file descriptor int fd of 2. So the API returns 0 on success and -1 on failure, okay. So here the pipe has a two end, okay. So one end is for the reading and another end is for the writing, okay. The process can read from fd0 and write to fd1, okay. So these two file descriptor you need to use in your application program. So if you want the process communicates with each other. A single process with the pipe is not very useful. So usually a parent process uses the pipes to communicate with its children, okay. So here if the parent want to communicate with the child, then the pipe concept is using. The next topic is symbolic link file API. A symbolic link is an indirect pointer to a file, unlike the hard links which pointed directly to the inode of the file, okay. So here the hard link pointed directly to the inode, okay. So if you observe, so in the link file, so if you create the link file, the inode number of both the file will be same, okay, because that is directly pointing to that file. So here the symbolic link file is indirectly pointing to a file, okay. So the original file may be in another file system, okay, and then you are creating that shortcut or the link in another file, Okay, so both have the different inode number. Symbolic links are developed to get around the limitations of hard link. Okay, to overcome the limitations of a hard link, so here we are using a symbolic link. Symbolic links can link file across the file system. Symbolic links can link directory file, so can link a directory file also, not to the regular file. Symbolic links always reference the latest version of the files to which they link. There are no file system limitations on a symbolic link. Symbolic links are typically used to move a file or entire directory, okay, to some other location on a system. Okay, so if you want to move one file or directory to another file system, then you can use your symbolic link. Okay, but so using a hard link, so it is not possible. So here in Unix system, the symbolic link is created, so using the API symlink. Okay, so here for symbolic link APIs there are three. First one is a symlink to create the symbolic link between the file or directory, and a read link, so reading that link so created, and lstat, okay, to access all the attributes of a link created to a file. Okay, so you need to use these API in your application program if you want to work with a symbolic link to creating another link or shortcut to a file.